Um, I will start my presentation. The title of this paper is a study of tank for liquid with taking into account the succession of filling up and running off. Uh, Tanks are used for storage of liquids in numerous applications in various branches of up-to-date engineering. This fact indicates that analyzing different aspects of the mechanical behavior of tanks with liquids is an important problem from both theoretical and practical point of view. Our attention here is concentrated to the analysis of stresses and strains in the wall of a tank for liquid with taking into account the succession of filling up and running off. The tank under consideration represents a circular cylindrical a circular cylinder of thin wall. The bottom of the tank is placed on a rigid base. The top of the tank is open. The tank has non-linear viscoelastic behavior. The wall of the tank is functionally graded. The material properties are distributed symmetrically with respect to the mid-surface of the wall. The viscoelastic behavior of the tank wall in the process of filling up and running off is treated by using a nonlinear stress-strain time relationship that accounts for the stress history. This relationship expresses the total strain as a function of stress and time. The change of the strain in the tank wall with time is analyzed in detail. The effects of various geometrical and material parameters on the stress in the tank wall are also evaluated and illustrated by various graphs. The tank under consideration here represents a circular cylinder with diameter d and height h. The wall of the tank is thin. The bottom of the tank is placed on a rigid base. The top of the tank is open. As already stated, our goal is to analyze stresses and strains in the wall of the tank with taking into account the succession of filling up and running off. First, the tank is slowly filled. This is shown in figure 1a. The liquid level H1 in the tank rises as given in equation number 1. In this equation, T is time. At time T1, the tank is completely full, as shown in figure 1b. After that, the tank is slowly emptied. The liquid level changes as given in equation number 3. At time T2, the tank is completely emptied. In the process of filling up and running off, the wall of the tank exhibits nonlinear viscoelastic behavior. The stress-strain time relationship used for treating the tank wall behavior is given in equation number 5. This equation is taken from the literature. In this equation, epsilon is the strain, sigma is the stress, B, delta, and phi are material parameters. As already stated, the tank wall is functionally graded in thickness with material properties distributed symmetrically about the mid-surface of the wall, as given in equation number 6. In this equation, the axis x is directed along the wall thickness. The origin of x is in the mid-surface. B is the wall thickness. Since the tank is thin-walled, B is negligible, small compared to the diameter of tank. BC and BW are the volumes of B in the mid-surface and in the surface of the wall. Lambda 1 is a parameter. The analysis begins with writing the condition of equilibrium along the normal towards the surface of the tank as given in equation number 8. Here Q is the pressure on the internal surface of the wall, sigma m and sigma p are the stresses in the wall in the meridian and hope directions. ds1, ds2, d theta and d phi are geometrical parameters related as given in equations 9 and 10. In these equations, rho m and rho p are the radiuses of the surfaces in meridional and hope directions, respectively. Since the tank is a circular cylindrical surface, we have dependencies given in equations number 11 and 12. In view of these relations, equations number 9 and 10 are transformed as given in equations number 13 and 14. Since the only support is the rigid base in the bottom of the tank, the stress in the wall along the meridian of the tank in vertical direction are zero. The pressure Q is obtained by applying equation number 16. Here gamma is the volumetric weight of the liquid. The vertical axis Z is defined in figure number 1. By inserting of equations number 13, 14, 15 and 16 in equation number 8, we obtain equation number 19. Then by substituting of equation 20 and 21 in equation 5, we obtain equation number 22. From this equation, we can derive dependency, which is given in equation number 23. Here we should note that for BC equal to BW equal to B, D equal to unit and phi equal to 0, equation number 19 transforms in equation number 24, which is exact match to the expression for stresses sigma p in a circular cylindrical linear elastic tank with a homogeneous wall. This circumstance is an indication for the correctness of the present solution, since at BC equal to BW equal to B, delta equal to unit and phi equal to 0, expression number 5 is transformed into the stress-strain dependency of a linear elastic homogeneous material. Next, we analyze the viscoelastic behavior of the tank wall during running off in the interval of time between T1 and T2. The pressure on the internal surface of the wall is obtained from equation number 16, where the liquid level is given in equation number 3. The stress-strain time relationship for the tank wall during running off is given in equation number 25. The change in strain in the tank wall over the time is analyzed and presented graphically. The influence of various geometrical and material parameters on the stress in the tank wall is also analyzed and illustrated with different graphs shown in the next figures. First, we analyze the change in the strain over time. This change is illustrated by the graphs shown in figure number 2. It can be seen in this figure that the strain rises when the tank is filled. The strain reaches its maximum at the time when the tank is completely full. In the process of running off, the strain continuously decreases. Next, the influence of the relative thickness and the volumetric weight of the liquid on the stress in the wall are studied. These influences are illustrated in figure number 3, where the graph of the dependency of the dimensionless stress on the volumetric weight of the liquid is presented at 3 relative thicknesses of the wall. By inspecting the graphs in figure number 3, we can observe that the stress rapidly grows when the volumetric weight of the liquid increases. Concerning the influence of the relative thickness, we see in figure number 3 that the stress reduces with growth of B to D ratio. The influence of the change of parameter B across the wall thickness on the stress is studied too. This influence can be evaluated in figure number 4, where the dimensionless stress is plotted against BW to BC ratio. The latter characterizes the change of B. Plots at 3 H to D ratios are shown in figure number 4 in order to examine the influence of the tank geometry. In figure number 4, it can be seen that increasing the ratio BW to BC leads to a decrease in the stress. However, growth of H to D ratio generates an increase of the stress. Finally, it should be mentioned that the analysis presented in this paper can be applied in structural design of tanks with liquids when the wall of the tanks exhibits nonlinear viscoelastic behavior. Thank you for your attention.